At the Royal International Air Tattoo 2025, held in the United Kingdom, Pakistan Air Force participated with its JF-17 Thunder, revealing important technical upgrades that had not been publicly confirmed before. The showcased variant demonstrated flight characteristics and system performance that marked a clear departure from previous iterations. Aviation analysts and observers noted specific improvements that directly indicated a change in propulsion architecture and electronic subsystem integration. The aircraft's acceleration, sustained climb rate, and top-end transonic transition suggested the integration of the Russian RD-93MA engine, an advanced evolution over the older RD-93 unit previously used in the Block 1 and 2 variants. The RD-93MA provides a significant thrust-to-weight increase, improved fuel efficiency at higher altitudes, and refined thermal management, which allows for more power-intensive mission systems. The specific performance envelope observed during the JF-17's aerial display, especially in post-vertical maneuvers and sustained energy retention across high G turns, clearly exceeded what the original RD-93 could deliver. The absence of visible black smoke trails, historically associated with earlier engine configurations, confirmed the presence of a redesigned combustion cycle and cleaner exhaust architecture, either from the MA variant or a high-efficiency turbofan alternative tested in secret phases. These propulsion improvements are directly tied to enhanced avionics and sensor loadouts. Greater onboard power generation translates into more stable operations of electronically scanned radar arrays and distributed electronic warfare systems. The JF-17 exhibited integrated sensor fusion behavior by rapidly shifting from tracking mode to simulated engagement during mock demonstrations, implying significant onboard computational throughput, heat dissipation capacity, and radar cooling support. The aircraft carried an airframe-conformal ASA radar with long-range multi-target tracking capability, tightly interfaced with its electronic support suite and helmet-mounted cueing system. Close analysis of the external stores during the event showed that the aircraft was rigged for multiple air-to-air and air-to-ground roles. External pylons supported dual racks, smart munitions, and active radar-guided missiles. The apparent payload capacity, load symmetry, and weight distribution reflected a revised airframe stress tolerance, possibly due to material improvements and load-bearing redesigns in key wing root sections. Additionally, carriage of heavier long-range weapons indicated an increase in maximum takeoff weight and aerodynamic balance in extended combat loadouts. Within defense circles, the most critical observation was the JF-17's ability to handle simultaneous electronic and kinetic missions under simulated interference conditions. Demonstration profiles hinted at onboard jamming systems operating across multiple bands while maintaining radar lock and communication integrity. These capabilities suggest integration of a multi-layered digital warfare backbone, similar in architecture to fifth-generation platforms, allowing the pilot to command radar, data links, jamming, and countermeasure modules without latency or cross-system interference. The engine's electrical margin appears capable of sustaining such demands, which confirms that the new power plant is driving not just propulsion, but overall platform survivability and network participation. Observers also noted the introduction of passive electronic emission detectors mounted along the dorsal spine and wing roots. These allow the JF-17 to track hostile radar sources without radiating its own signal, greatly increasing situational awareness and threat reaction timing. The fusion of such systems with the radar and data link layer turns the aircraft into a multi-domain reconnaissance and strike vector. Ground-based observers at the show noted brief uplinks to a nearby Pakistani mission control node operating a simulated combat cloud, confirming the JF-17's full compatibility with network-centric doctrine and live data sharing. Another major development involved the evolution of armament standardization. Brief static presentations revealed that the JF-17 was loaded with air-to-air missiles that were neither Russian nor Chinese in origin, strongly implying the use of indigenous beyond visual range and short-range missiles under confidential testing. The apparent presence of canard fin and dual pulse motor designs with dual mode seekers indicated Pakistan's indigenous missile program has moved beyond early prototypes into airborne test integration. The move to replace imported weapons with indigenous ones is consistent with the broader Project PFX strategy to gain sovereignty over both avionics and weapons architecture. The aircraft's digital control systems also showed greater finesse during flyby routines. High angle of attack maneuvers and energy recoveries suggest a revised flight control computer with predictive authority mapping and redundant control loops. Pilots were to execute nonlinear throttle transitions and roll-yaw combinations without visible corrections, which only occurs in highly integrated flight management systems where digital fly-by-wire and engine control units communicate through deterministic architecture. This software-centric reliability also ensures safe envelope expansion as Pakistan moves toward more aggressive weapons testing under PFX alpha trials. From a geopolitical perspective, the timing and venue of this capability revelation hold strategic weight. The United Kingdom's Royal International Air Tattoo is one of the few global platforms that bring together defense observers, aerospace specialists, and strategic planners under a single airspace. By selecting this platform to showcase technical maturity and digital avionics sovereignty, Pakistan is sending a deliberate message of capability evolution that bypasses traditional dependency on Russian or Chinese avionics ecosystems. It highlights a shift in indigenous systems, integration capacity, and the ability to field hardware that matches or exceeds regional fourth-plus generation benchmarks. The combination of the new propulsion, avionics, electronic warfare, and sensor fusion capacities effectively redefines the JF-17 into a transgenerational platform. While originally designed as a cost-effective multi-role platform, the aircraft's current form represents a platform architecture built to absorb next-generation technologies. The power plant's ability to support ESA radar, distributed computing, dual-mode radar, onboard signal jamming, and passive warning systems turns it into a real-time combat management node rather than just a fast-moving airframe. As Project PFX progresses, the JF-17 will serve as the testbed for both systems validation and doctrine evolution. Each engine, radar, missile, and software iteration will be fielded, tested, evaluated, and refined on a live airframe that already has operational credibility. The shift from foreign to domestic air-to-air missile testing, both in short-range and long-range domains, will allow tighter software-hardware loops, faster correction cycles, and sovereign optimization. The aircraft's mission computer is designed to adapt these new weapons through modular integration protocols, allowing Pakistan to bypass legacy supplier dependencies and field custom-configured weapon sets across varying platforms. The 2025 event represents a definitive milestone in the life cycle of the JF-17. From a platform once dependent on externally sourced engines, sensors, and weapons, it is now morphing into a low-cost, sovereign air dominance node optimized for layered threats, hybrid warfare, and deep strike coordination. The pathway laid out at this event directly supports the future doctrines of Pakistan Air Force under PFX Alpha, where digital dominance, integrated kill chains, and electronic supremacy are not aspirational targets, but operational baselines.